In this video, we are going to cover section 5.5. This is going to be about inverse trig functions. And before we start talking about inverse trig functions, we need to do a little bit of review from pre-calculus 1. Okay. And so you might remember from pre-calculus 1, or maybe even algebra course, that if a horizontal line intersects the graph of a function more than once, that function does not have an inverse function. Okay. So the idea is if a function has an inverse, we don't want it to just be an inverse. We want it to be an inverse function. We want it to only give us one value out. Okay. And we're going to kind of see how that comes to play here soon. But before we do that, let's just make a quick sketch of what things might have an inverse function versus what things might not. Okay. And we'll just go with some really basic functions here. So we could, for instance, say have like an exponential. You won't be able to find a horizontal line that goes through this graph more than once. Okay. So this one here would have an inverse function. Okay. And now something that doesn't, well, we're going to be able to find a horizontal line that goes through it at that goes through it more than once. That's what I'm looking for. Let me try that again. There we go. So a good example of something that won't have an inverse function would be, say, a parabola. Okay. For instance, we could find this horizontal line right here that goes through it, and you can see it goes through it again more than once. Okay. Which, as opposed to over here, every horizontal line I sketch on this side will only go through the graph once, never more. Okay. So that second one that we sketched does not have an inverse function. Another important thing about inverses is that if f of x is equal to y, then if you take f inverse of y, that should give you x. Okay. So all of the inputs of the function f are now the outputs for the inverse. And all of the outputs for the function f are now the inputs for the inverse. Now, the reason we're talking about this is it ends up that none of our trig functions pass the horizontal line test. Because of their periodic nature, they hit the same y values over and over and over and over. Okay. So they don't even come close to passing the horizontal line test. And thus, none of them have an inverse function. But I want to be really specific here. They don't have one on their domain. Okay. So is what we're going to do is we're going to restrict their domains to sections where these functions do pass the horizontal line test. Okay. So let's write in what we're going to do. We shall restrict the domain of each trig function to an interval, again, where they pass the horizontal line test. So before we start with the inverse, I'm actually going to have us maybe make maybe like a little table of values, or maybe actually even a look at the graph. That might even be better. Okay. So if we were to look at the graph, say, of sine of x, okay, I'm only going to look at it over a certain region. Let me make a slightly bigger set of axes here, though. Okay. There we go. So if we were to go up one, down one, I just wanted to move that down a little bit more. There we go. And we're only going to go from minus pi over 2 to pi over 2. Let's see what that looks like here. Pi over 2, and then minus pi over 2. There we go. So if you were to graph sine of x on this interval, we know sine is 0 at 0. We know at pi over 2 it's 1. And we know at minus pi over 2 it's 0. And so if we go ahead and make this now look like a sine curve, let me see if I can make that a little bit cleaner looking. There we go. So this is the part of the sine function we're going to be working with. And you can see it does indeed pass the horizontal line test. Is what this is going to tell us, though, is that sine inverse is only going to be able to give us angles that are in between minus pi over 2 and pi over 2. So that being said, regular trig functions take angles as inputs. Inverse trig functions give angles as outputs. Okay. So let's go ahead and move our little sketch of sine over. Maybe I'll just note up here that this was y equals sine of x. And I'll scoot us back over, and we're going to make ourselves two little tables here. Okay. So when we're talking about, say, sine of x, is what I've just mentioned is that we're going to restrict its domain. We're going to only look at minus pi over 2 to pi over 2. Okay. So this is that restriction that we're talking about. Maybe I can arrow to it. Let's see. Let's go like this. But notice that its range, if we go back, still covers the normal range of sine, which is minus 1 to 1. Okay. And you might remember something about inverse trig functions here. And that is the domain and range of these two functions should swap. So the domain for sine inverse is minus 1 to 1. Okay. This means if you plug in anything bigger than 1 or smaller than negative 1 into sine inverse on your calculator, it will give you an error message letting you know that's not in the domain. Okay. And our range is minus pi over 2 to pi over 2. Okay. Now, this is somewhat unfortunate because that means if we're searching for an angle that's not in between these two values, we're going to have to be really careful when we're applying sine inverse. Okay. Now, we don't know how to do that yet, but we will eventually see. Okay. So now here's the next thing. Now we want to make a sketch. Okay. Well, I think it might be nice to maybe have a table of values here. One for sine and then one for sine inverse. And so again, do remember that these are going to switch. And is what I mean by switch is the x's and the y's are going to swap between these two. Let me just try and scoot that down. All right, so let's call this maybe x. We'll call this y equals sine x, and this y equals x, and then y equals sine inverse of x. Okay. So from minus pi over 2 to pi over 2, there were only a few interesting values we had there. So we had minus pi over 2, we had 0, and then pi over 2. And we found the y values. They were minus 1, 0, and 1. So what's going to happen then with sine inverse is now the inputs are minus 1, 0, and 1, but the outputs instead are the angles. There we go. All right, so now I want us to try to graph this. And you can see in the x direction, we're just thinking about ones and minus ones here. So I'm going to go ahead here, and maybe I'll call this 1 right here. Debating whether I want to go a little further out. That could be 1 there. This could be our minus 1. Okay. Additionally, so that was the x direction. In the y, we just need to go from minus pi over 2 to pi over 2. So down here, I'm going to put in, how about the minus pi over 2? Let's see if pi over 2 is a number that's bigger than or smaller than 1. Let's see. Pi over 2. It should be bigger than 1. You can see it's about 1.5. Okay. So my pi over 2s, I'm going to maybe make those go up a little bit higher. So if this is 1, maybe this could be 1.5-ish. I'm going to actually write it in as pi over 2. And then down here, we'll put in our minus pi over 2. And we already have the values that we want to plot. We have minus 1, comma, minus pi over 2. We have 0, 0, and then we have 1, comma, pi over 2. Okay. Now, the hard part here is going to be connecting these dots with something that looks like sine inverse. Okay. So there's a couple ways that we could think about this, but one thing that's not a bad idea is we could kind of take a peek at how this looks on the calculator. Okay. And I'll show you that there's actually a trick. We could have just sketched sine in first, and then we could have sketched its inverse in more easily. Okay. So I want you to check your mode and make sure you're in radians here. Then in our y equals, let's go ahead and put in sine inverse of x. Okay. And then for our, let's say for our x values, we'll still go minus 1 to 1. And I just counted by ones when I did that, so leave it like that. In the y's, we just needed to go minus pi over 2 to pi over 2, and we were counting by pi over 2's. So I'll make that my y scale as well. Okay. And so we can go ahead and hit graph here, and we'll see what it looks like. Okay. It looks like I have a little chart that's on here. Let me actually go and shut that off so that it's not getting in the way of our image. Okay. So this is what it's going to look like. Okay. Let's go ahead and sketch that in. So it looks something like that. Okay. So I mentioned that there's kind of a trick for sketching this though. Okay. So if I had sketched sine of x first, it ends up that every function and its inverse are reflections across the line y equals x. So let me put the line y equals x in here first. Oop. Here we go. So, and then I'll graph it. So if I were to graph in here now sine of x, it's going to get reflected across that red line you're seeing there. So I'm going to go in here and I'll put in sine of x so you can see. Okay. I know it's kind of hard to tell, but you can kind of see that black curve is reflected across the line, the red line there, to give us the blue one. Okay. Now I could zoom out here a little bit. Is what you're going to notice again is that blue one, the inverse, has a restricted domain. Okay, it's not going to go as far as sine of x is going to. So if I actually go in here to my window and maybe extend this a little bit, let's maybe say minus pi to pi, maybe by pi, let's go pi over 2's. And I think I'll just leave the y's the same, okay? So now you can see that that black curve really is the sine function, and it just looks like a reflection of the blue one, its inverse trig function. Other than it stops soon. Okay. I'm going to make the y's a little bit bigger too. Let's maybe go minus, let's do minus pi to pi there too. Why not? Okay. And I'll just leave that y scale as pi over 2. And if we look, there it is. Okay. So your inverse trig function has a very small graph. Okay. Or your inverse sine function has a very small graph. All right. So there's that. Okay. So we're actually not going to do a lot graphically with these inverse trig functions. Okay. There, but we will do plenty with them. But usually, it's not going to be graphical in nature like this. Okay. So let's take a look now at cosine inverse, and we're going to discover here in a moment what the restricted domain and range are going to be here as well. So for cosine of x, that restricted domain is actually 0 to pi. Okay. And the reason it's not minus pi over 2 to pi over 2 like sine is well, cosine won't pass the horizontal line test on that interval, but it will pass it on this one. Okay. And so maybe we'll make ourselves a little sketch of cosine of x again here. Not a bad idea, at least with the restricted domain. And you know what? I guess we don't really need to do that. We can skip that part. Okay. Let's write in the range though. So is what you'll see if we were to graph this cosine of x is not only that it passes the horizontal line test on this interval, but also it goes through the values minus 1 to 1. Meaning it covers every y value that it would cover if we weren't looking at the restricted domain. Okay. Then, if we think about the inverse function here, remember the domain and range should swap here. So we'll have minus 1 to 1 and 0 to pi. There we go. And I'm going to try to make a sketch of this too in the, what is it, the x direction now. I only need to go minus 1 to 1 for our inverse trig function. So let's see. Let's go. I'm going to go a little further in. Let's call this right here minus 1. And we'll call this positive 1. Okay. And then as far as the range goes, right, this just says 0 to pi. So maybe all the way up here, maybe I could call this pi. And maybe we can make a table of values to get started here. But I think we're also going to probably want maybe a pi over 2 in here. We'll see. So if I were to make us a table of values on that interval, I'm just going to use my quarter points. 0, 0, pi over 2, and pi. And I think I'm going to scoot this a little bit this way so I have room to write y equals cosine of x here. So cosine of 0 is 1, cosine of pi over 2 is 0, and cosine of pi is minus 1. So now we can look at cosine inverse, right? We're just going to switch all of those x's and y's here in a second. Right, and so what do we have here? We have 0, pi over 2, and minus 1. And let's go ahead and put these in. Okay. So 1 comma 0, that's right here. 0 comma pi over 2, that's right here. And minus 1 comma minus 1. So I actually need, let's see. Sorry, you can hear my dog barking in the back here. I wrote in the wrong value over here. It should be a pi. Let me fix that. There we go. So I just adjusted this value here. So minus 1 comma pi. Let's see. Yeah, minus 1 pi. That's going to be up here. There we go. And I apparently deleted my 1 comma 0. Let me put that in here. So again, if you're trying to think about the shape here, one option is that you could graph the curve cosine of x and the line y equals x and just simply reflect it across that line for this region. Okay. To make things a little faster and a little cleaner, let's do it on the calculator. Okay. So this time we want cosine inverse. So I'll hit second and then cosine for my cosine inverse. And we could leave in the line y equals x if we want to. Let's maybe leave it in for a second here. So we need to reflect that blue curve you're seeing there across that red line. And so the question is, well, what's that going to look like? Or actually, we don't need to do that. The blue is the reflected version of the original function, but I want you to still be able to see it. So let me put in cosine of x here, and then we'll delete it and sketch um, the inverse. Yeah. So it may be hard to tell here, but if you grab a certain section of, again, the cosine function and reflect it across the line y equals x, you will get that blue one. Okay. So let's go ahead and try to make that blue curve there. So this should look something like this. There we go. So there's our inverse cosine. And the last one we're actually going to do is inverse tangent. We're not going to bother with inverse secant, inverse cosecant, or inverse cotangent because you can always rewrite those functions in terms of sine, cosine, or tangent, and then we can just use the inverse functions for sine, cosine, and tangent. Okay, so the last one here. So let's go ahead and write in what our restricted domain is this time. And then we'll eventually be able to write in the domain and range for both of these. Okay. So we're going to restrict this to be between minus pi over 2 and pi over 2. But you can actually see that this time I'm using parentheses, meaning that pi over 2 and minus pi over 2 aren't actually included in the interval. But if you were to look at the graph of tangent of x over this interval, well, you'll notice it has two vertical asymptotes, one at pi over 2, one at minus pi over 2. So this thing has a range still, just like its normal range. It's minus infinity to infinity. But let's just again note, this is the restricted domain. This is the restriction we're making. Okay. So then if we switch these, that means that the domain for tangent inverse is actually all real numbers. And its range is just numbers between minus pi over 2 and pi over 2. Right? So next is what we could do is we could once again maybe make like a little table of values. So let's do that. If we can't really plug in that many things here over that interval. Let's see what we can plug in. So I know we can plug in a minus pi over 4, a 0, and a positive pi over 4. And you might remember it's minus 1 here, it's 0 here, and it's 1 here if we're talking about tangent. And so when I go to write in my inverse tangent here, I now am again just going to switch the domains and ranges here, or just switch the x's and the y's, I suppose, in this case. So if I want to sketch at least those points, in the x direction, I need to go minus 1 to 1. So again, you might be noticing here, right, our range for the inverse trig function is stuck in between minus pi over 2 and pi over 2. Okay. And it may not be obvious at the moment, but there's actually going to be horizontal asymptotes here. It's never going to reach pi over 2, and it's never going to reach minus pi over 2. There we go. So let's put in our 3 points. So we have minus 1 comma minus pi over 4. We have 0 comma 0, and then 1 comma 1. Okay. So again, is what's going to happen here, and we'll see it on the calculator here in a second. Let's see. It should wind up looking something like this. It should look like tangent reflected across the line y equals x. Okay. And we can verify this again on the calculator. So I can come over here and I can type in instead second and then tangent for tangent inverse. I have my x here, and then I can make this one tangent. Let's go ahead and graph and see what we wind up with. Okay. So in the black there is what you're seeing is tangent. Okay. In the red, you're seeing the line y equals x, and in the blue is the inverse tangent. Okay. And if you want to see that it really does have those asymptotes that we were talking about there in the blue, we could get rid of some of this, and I could maybe make this a pi over 2. I'm just putting in a horizontal line where I know the asymptote is, and I'll put in another one where the other asymptote is. And then in the, let's go into the window, and let's just maybe make this like minus 30 to 30. That's a pretty far range here. I'll just count by ones. And then in the y direction, we don't really need to go past where any further than we already are. Minus pi to pi will work just fine here. So let's go ahead and hit graph. Okay. And you can see that that blue curve, which is our inverse tangent, does actually have two horizontal asymptotes, one at minus pi over 2 and one at positive pi over 2. All right. Now, here's the deal. So it's nice and all to have these graphs, but how are we really going to be using this? And so one of the most important things you need to know from up there is, what are these restricted domains? Because um, we need to know what kind of angles we can get out of our inverse trig functions. Okay. So I usually just make a little diagram here to help myself remember. I don't have to really look at it anymore, but when I was first learning this, I definitely was always thinking about this. So you may have noticed both sine inverse and cosine inverse were able to give us angles between minus pi over 2 and pi over 2. So when we're talking about sine inverse and tangent inverse, we'll be in these two quadrants here. Okay. And then when we're thinking about cosine, that's the one that really differs. That one's 0 to pi. So cosine inverse can only give you angles from, again, 0 to pi. So let's kind of just write in those important angles here. So this is 0. This one down here, we're thinking about it as minus pi over 2. And then finally up here, we have positive pi over 2. And then over here, we have pi. So I would highly recommend, making sure you remember what quadrants these trig functions can give us angles in. Otherwise, it's really hard to work with the inverse trig functions properly. All right, so let's start off right here. Okay. It says to find the exact value of each one of these trig functions. Okay. So one way to think about this is we want to know for what theta does sine of theta equal the square root of 3 over 2? Okay. Now, if we weren't working with the inverse function here, there would actually be an infinite number of answers. Okay. Now, remember though, we are working with an inverse trig function here. This sine inverse can only give us angles between minus pi over 2 and pi over 2. So we're going to try to find the square root of 3 over 2 on our unit circle. And since we're thinking about sine, we want it to be a y value. Okay. And so let's go ahead and highlight where that is. Specifically where the y value is root 3 over 2. Okay. So there's two spots, okay? But remember, again, sine inverse can only give us angles that are between minus pi over 2 and pi over 2. This is not in between minus pi over 2 and pi over 2. However, this one is. So our answer here is going to be pi over 3. So we can go over here and we can record that. Let's see. But yeah, as we were answering it, this question in the green is what we were trying to answer. There we go. All right, now we're going to do the same thing, but with negative the square root of 3 over 2. Okay. And we're going to have the same exact issue every time we do these, but let's go to that unit circle and find those minus root 3 over 2's. They should be at the bottom of the unit circle here. So if I scoot down here, you can see here's one y value and another y value where we get minus root 3 over 2. Okay. Now, do remember, though, that it has to be between minus pi over 2 and pi over 2, which is up here. Okay. So in other words, the angle that we're going to record is going to be an angle that's either here in quadrant 4 or one that's in quadrant 1. Okay. So it can't be this one. So that only leaves us with this one here. So now here's the confusing part. you see that number 5 pi over 3? That is not what you want to record. Again, that angle is not an angle between minus pi over 2 and pi over 2. But if you were to write down the negative version of some of these angles here, let's maybe do that. Okay. Like this 11 pi over 6 here. Maybe I'll go like this. That would be equivalent to minus pi over 6. You could figure that out by subtracting 2 pi from 11 pi over 6. Similarly, this one right here, this would be minus pi over 4. And lastly, this one here, the one that we are really concerned with, is minus pi over 3. And so we can go ahead now and we'll record that. Okay. Let's see. Yeah. All right. And you should be able to check these on the calculator. For instance, if I were to do, say, sine inverse of, what was it? We started off with the square root of 3 over 2. Making sure you're still in radians. Okay. You can see I'm getting this 1.047197551. Okay. So the question is that equal to what we wrote, pi over 3? So if I type in pi over 3, you'll see we get the exact same decimal approximation. So we know we've done this right. Okay. And you could do the same thing with the one with the negative. Insert the negative there. And if I type in minus pi over 3, again, you'll see we have the same decimal approximation. So we're doing fine so far. Okay. All right. Then for cosine inverse, okay, this can only give us angles between 0 and pi. Okay. We'll want to keep that in mind as we go and look for the theta such that the x value is minus 1/2. So let's go do that. So our x value, I'm going to just get rid of some of this here. Here we go. So if the x value is minus 1/2, I see this one here. And I see this one here. Okay. Now, only one of those two highlighted ones is between 0 and pi. Okay. Right? This angle 4 pi over 3, that's bigger than pi. So that can't be the one. So our answer here must be the 2 pi over 3. Okay. And so we'll go record that. And again, you can check that. You can say, okay, cosine inverse of minus 1/2, I believe it was. And we got and then we got 2 pi over 3. Let's see if that's equivalent. Okay, so those are equivalent. Okay. So that's looking good too. Now, tangent is a little bit more challenging. Okay. So for one, we're still going to have to keep in mind that we're looking for angles between minus pi over 2 and pi over 2. But the unfortunate part is we need to find a ratio of minus root 3 over 3 on the unit circle. So for one, again, when we're thinking about tangent, angles must be between minus pi over 2 and pi over 2, meaning that we are in either quadrants 1 or 4. Okay. Well, in quadrant 1, if you do y over x, well, all of those are positive. However, in the fourth quadrant, we will get a negative, which is good because we were asked to find tangent inverse. Let's just write down what it was. Tangent inverse of this minus root 3 over 3. So we need to figure out which one of these y over x's will give us that. Okay. So we come down here. Let's just start with this one. So if I do y over x here, I get minus 1/2 over the square root of 3 over 2, which I can then simplify. That's 2 over root 3 times, let me fix that. We have minus 1/2 times the reciprocal of root 3 over 2. And so that actually simplifies to minus 1 over the square root of 3. And then you could rationalize the denominator, making that root 3 over 3. Okay. So this ends up being the angle that gives us that ratio. Okay. But remember, again, between minus pi over 2 and pi over 2, 11 pi over 6 is bigger than pi over 2. We need to write down the negative version of this angle. Okay. Or in other words, subtract 2 pi from this. And so if we do that, that'll give us negative pi over 6. Now, I didn't know that this was going to be the one that gave me the answer. It could have easily been this one. But it definitely wasn't going to be this one, because if you do y over x with 7 pi over 4, you get minus 1. Okay. So I knew it had to be either minus pi over 6 or minus pi over 3 is my answer. Okay. Let's go over here and fill that in. So what do we say? Minus pi over 6. Okay. And we'll go ahead and we'll check that one too. So tangent inverse of minus the square root of 3 divided by 3. And make sure that that is the right thing there. Yeah, okay. And so then we said that we think this is equivalent to minus pi over 6. And you can see, again, same decimal approximation. All right, and so I just have a couple more problems really for us to do here. But something interesting happens with our inverse functions. So we're not used to inverse functions that are created from restricting the domain of the original function. We've never seen that happen before. So it can create really strange things. Okay. And I think it might be better to just jump right into these two questions, and then we can go fill that out. Okay. So if you were to evaluate this and you didn't know exactly how inverse trig functions worked, well, then you could start evaluating these from the inside out. You could say, okay, well, I first want to figure out what cosine of 5 pi over 4 is. So I go over to my unit circle. I can find that 5 pi over 4. It's right here. And so is what that tells me is that cosine is minus the square root of 2 over 2 at that angle. Okay. So I can write in here minus root 2 over 2. And then when I go to evaluate cosine inverse, remember, I need to get an angle between 0 and pi. Cosine inverse gives us angles between 0 and pi. So now I'm going to go back over here to my unit circle, and I'm only going to be looking at the angles between 0 and pi. Okay. And specifically, if I can make this pop up here too, I want to find minus the square root of 2 over 2. Okay. So minus root 2 over 2, that's right here. Okay. And again, I can't use this one down here because it's not between 0 and pi. So is what we're getting then as our angle is actually 3 pi over 4. So this is really interesting. We have probably never seen some function and its inverse composed, and the input and output here being different numbers. Okay. So this happens sometimes when you're working with the inverse trig functions, and well, sometimes it doesn't. Okay. And we'll talk about when it happens and when it doesn't after we do this one here. Okay. So you can probably guess, I don't think it's going to happen on this one, that strange thing. Okay. So again, working from the inside out, sine of pi over 6 is 1/2. And so then I need to go to my unit circle, find an angle between 0 and, or sorry, I need to find an angle between minus pi over 2 and pi over 2. Well, if you go and do that, is what you're going to find is that that angle is indeed pi over 6. Okay. So sometimes these inverse trig functions undo each other, and sometimes they don't. Okay. So we're going to go kind of summarize when it happens up above, but there's no reason that you have to memorize what we write up above, because you can always do this like this. Okay. And let's just verify that these two worked out properly. So what we said, or at least one of them, cosine inverse of cosine of 5 pi over 4. And we said that that should be equal to 3 pi over 4. And again, you can see that those are equivalent. Okay. And what was our other one? It was sine inverse of sine of pi over 6. Okay. Which we said would be pi over 6. And you can see now that that is the case. So everything looks good. All right. So when it comes to these, I'm going to write exactly what you think over here. I'm going to say, well, this one's sine of x. This one's sine of x, cosine of x, cosine of x, and then tangent of x and tangent of x. But there's going to be a caveat. I'm writing actually the wrong thing here. If they undo each other, right, this would give us an x and x. So all these actually give us x. Okay. But time for the caveat. We'll see it eventually. Yeah. So sine inverse itself, right, can only give us angles between 0 or minus pi over 2 and pi over 2. Okay. That's not really problematic here because you can take sine of any angle. Okay. So this one here is actually for all x. It's this direction where we're going to have the issue. Okay. So I can plug any angle I want into sine, okay, but sine inverse will only output angles between minus pi over 2 and pi over 2. So is what I'm going to have to say here is this is for x in the interval from minus pi over 2 to pi over 2. Okay. And this is exactly what we experienced in the second part down here is pi over 6 was in between minus pi over 2 and pi over 2. And our inverse trig functions worked exactly how we thought they would work here. If it was outside of that, it wouldn't work the way we were expecting. Okay, and maybe we'll be able to say that here in a minute about this one. Okay. All right, so for cosine of cosine inverse of x, well, we can take cosine inverse of x, and then you can take cosine of any angle. So this one's going to work fine for all x. I should be a little bit more specific when I say for all x, okay? Because you might be asking yourself, well, what kind of x's can you actually plug into sine inverse and cosine inverse? Well, those are technically in between -1 and 1. So maybe I'll change that on this other one. If we go outside of 1 and -1, it's not that these trig functions aren't going to work the way we expect. They're just going to be undefined. Cosine inverse of, say, 3. Let's see what actually happens when you do that. Okay. So if you try to do cosine inverse of 3, you get an error. Okay. Right? It says error domain because that number is not in the domain. I'm just going to hit quit and delete what I have there so far. Okay. For this next set, this is again the problematic one where it may not work as you expect. Okay. So as long as we're in that restricted domain that we've been thinking about, which is from 0 to pi, everything's okay. Outside of that, you'll get a different value. So for instance, 5 pi over 4 is bigger than pi. And that's why this didn't give us 5 pi over 4 back. Okay. And then if we fill in these last two, this is for x in. And so when we're thinking about tangent inverse, you can actually plug in any number into tangent inverse. Okay. Yeah, let's see. So this one's not going to create actually any issues at all. Okay. On the other hand, the next one will. Okay, because again, tangent inverse can only give us angles that are between minus pi over 2 and pi over 2. Okay, so there's kind of the summary of when these functions essentially cancel each other out. Okay? Like I said, you don't need to memorize it though, because you can just try to evaluate these from the inside out and it'll always work. Okay? Right. And so that wraps up 5.5 here.